and welcome back to Astronomy News with the Cosmic Companion. This week we're joined by Dr. Maciek Wielgus, astronomer at Harvard University, speaking to us from Gdansk, Poland. We'll discuss his work revealing glittering around the supermassive black hole at the center of the M87 galaxy. But first, we look at a new study identifying 24 exoplanets that appear to be even friendlier to life than Earth. We also see how superflares, powerful eruptions from stars, behave and learn how they might affect alien life on other worlds. Then we take a look at OSIRIS-REx, NASA's first attempt to collect material from an asteroid, as the revolutionary spacecraft readies to touch the surface of the asteroid Bennu. Astronomers from Washington State University recently examined data from 4,500 known exoplanets, searching for worlds where life is likely to have developed. The researchers found 24 worlds which could be even more habitable than Earth. Such worlds would likely be larger, warmer, and wetter than our home planet, orbiting stars with exceptionally long lifespans. These conditions could drive natural selection, increasing chances for the development of life on alien worlds, researchers speculate. An examination of 27 superflares erupting from stars showed these events release significantly more ultraviolet energy than expected. Such eruptions releasing vast, powerful discharges of radiation could wipe out life on alien worlds. However, these eruptions were found to last just around 15 minutes, reducing the amount of time that life forms would be exposed to these potentially catastrophic events. This could greatly increase chances of life developing on worlds which orbit close to small, cool stars, researchers speculate. NASA is preparing for their first sample collection mission to an asteroid as OSIRIS-REx readies for a planned touchdown on the surface of Bennu. The asteroid is known to be composed partly of carbon-rich organic materials. The first attempt to collect material from Bennu will be made on October 20th, with the sample scheduled to arrive at Earth in September of 2023. This mission could potentially help explain how the building blocks of life first formed on Earth.
Looking deep into the universe, we see backwards in time, and the oldest light in the universe holds secrets to how everything around us will, one day, end. Meanwhile, stars, planets, and galaxies dance in an intricate ballet, occasionally giving birth to life. We are a fledgling species, just beginning to visit other worlds. We are a way for the universe to understand itself. The Cosmic Companion strives to bring the universe down to Earth, and we depend on your help to make it happen. For information on subscriptions and ways to donate to this program, please visit thecosmiccompanion.net. Thank you.
This week on Astronomy News with the Cosmic Companion, we talked to Dr. Maciek Wielgus, astronomer at Harvard University, who is joining us from Gdansk, Poland. We'll be discussing his work revealing glittering around the supermassive black hole at the center of the M87 galaxy. This week on Astronomy News with the Cosmic Companion, we are happy to be joined by Dr. Maciek Wielgus,
Very well.
He is, thank you, he's an astronomer at Harvard University and works on the Earth Horizon Telescope. He recently made an interesting discovery about a nearby supermassive black hole. Welcome to the show, Maciek.
Hello, thanks for having me.
Yeah, thank you. So just simple question. You just tell us a little bit about what is M87, what it is you found there, and about its supermassive black hole.
All right, so M87 is a giant galaxy in a Virgo cluster. It's the very center of mass of the Virgo cluster. It's really huge. And for a huge galaxy, it harbors a huge black hole in its center. So this is what we named M87 star. This is the center of the M87 galaxy. And that's the black hole that many people hopefully are familiar with, because that's the one that we made the first image of last year. So last year, with this Event Horizon telescope, the assembled telescope of the effective diameter equal about to the diameter of the Earth, we finally got the resolving power to see the structure of the accretion flow, to really see this black hole on the spatial scale that can resolve the event horizon scale. And we saw this bright ring, and the current results, the results that came out just on 23rd of September this year, are about monitoring this object for many years, starting in 2009 all the way to 2017, and actually seeing that there is a little bit of interesting behavior in the object.
And what is this interesting behavior that you're seeing?
So there are a couple of aspects of that. One interesting thing is that actually we did confirm the morphology of this source, meaning we see that the old data were consistent with this ring-like appearance. So that's a big thing, because if we saw that there was definitely no ring in the past, or if we saw that there was a ring, but it was half times larger, twice as small, or whatever, that would immediately tell us that, well, everything we thought that it is must be wrong. Our interpretation with the supermassive black hole must be wrong. So fortunately, that turned out not to be the case. We confirmed this consistency. But on the other hand, when we tried to fit where is the location of this bright side of the crescent, we noticed that it's changing in time. It's changing in time quite a lot, probably more than many of the people would intuitively expect, but it turns out it's consistent with the expectations from the numerical simulations. And what is wobbling, this is not a black hole moving, this is the gas circling around it, falling into the event horizon. This flow is turbulent, it is violently chaotic, and this chaos in the flow makes this appearance, this bright part, to shift around.
So it's actually the gas itself that's giving off. Is it actually giving off more or less energy because of interactions, or is it just appearing that way because of its movement?
So what's going on? The motion itself is one thing. The fact that it's circling around the black hole and finally falling into the event horizon, that is one thing. But the other thing is this overwhelming turbulence in the behavior of this flow. So if it was a nice steady state flow, there was no turbulence, no chaos in its behavior, we would see a constant image. We don't, as we confirmed now, so we see that there is something going on. And this thing is really the subtle changes, or maybe not even so subtle changes, in local density, in local temperature, in local values of the magnetic field, and all together they make this pattern of chaotic behavior. Because the more of density we have, the larger the temperature, the more magnetic field, the more radiation we will see. The radiation is coming from so-called synchrotron radiation process. So these are electrons in the electric field, accelerating in the electric field. So the more electrons we have, the stronger the magnetic field, the more radiation we will see. So it could be that in one point in time, on one side of this flow, there is more matter, more magnetic field because of how turbulent it is, but at the other moment. And this is all this wobbling happening.
It's fascinating. So why is it that we are looking at the black hole within M87 when we know that every galaxy has a supermassive black hole, including the Milky Way?
So it turns out that, well, there are two important numbers to consider. One is the size of this black hole, and the other is the distance towards it. And of course, how large it is, as we see it in the sky, it depends on the ratio of these two factors. So it needs to be large, but it also needs to be close, as close as possible. And it turns out that this ratio is very good for M87 because it is huge. It is 6.5 billion solar masses, and it's not too far away. Meaning it's 55 million light years away, which sounds like a lot. It is a lot, but in the cosmological scale of the universe, it's still kind of our neighborhood. So on the other hand, the supermassive black hole in the center of our galaxy, this one is lighter by 1500, by a factor of 1500. So that means it's smaller in terms of size in kilometers. The event horizon is smaller by 1500 factor. It is fortunately also about 1500 times closer to us. So the ratio remains very similar. So this is the other object that we can hope to ever resolve, Sagittarius A star, the center of our galaxy. There are only two objects at the moment that have this ratio so good that it's within our resolution capabilities.
Right, right. Something similar happening, of course, with Betelgeuse, you know, where the only two stars that we can actually see the surface of are our sun, because it's smaller, but much, much closer, and Betelgeuse, which is much further away, but much larger.
That's exactly the same thing.
Right. So talking about the similarities between Sag A star at the center of the Milky Way and the supermassive black hole named M87, we'd also then expect a similar twinkling to be going on within our own local black hole?
We absolutely do, but actually it's even more than that. Because of this ratio in masses, because of the fact that the Sagittarius A star is 1500 times smaller, it means that also characteristic time scale is 1500 times smaller. So what it means, characteristic time for M87 is about 9 hours. I'm just giving some characteristic number associated to the source. So the same associated number would be about 20 seconds for Sagittarius A star. So let's say that this characteristic number is really for how long the source doesn't change at all. This is actually related to the light crossing time. How quickly can information move from one side of the source to the other side? So nothing can change faster than that. That is our argument, because information cannot propagate faster than light. So what it means is that during one night, M87 should pretty much stand still because of this characteristic timescale. And on the other hand, Sagittarius A star, our galactic center, it should be varying like crazy because this characteristic timescale is 1500 times less. It poses a lot of problems for the method that we are using to create those images. It's like you were trying to take a photograph, but you had to wait for a couple of hours to get enough information to create this photograph. But the person you are trying to photograph, they do not really want to stand still for 9 hours. So M87 doesn't mind. M87 says, yes, I will stand still for 9 hours, don't worry. But M87 says, well, 20 seconds, it's as long as I can in one place. And that is the main difference. Everything around Sagittarius A star is happening 1,500 times faster than around M87. This is why we have the data from such a star. We recorded them at the same campaign in 2017 as we did M87 data, but it takes so much more time to analyze them and to build up this understanding to be able to share it with the world. Main reason is exactly this extreme time variability of the Sagittarius A star.
And can you tell us a little bit about the Earth Horizon Telescope and what it is that makes that network so special?
So the name is Event Horizon Telescope.
Oh.
And this is the international, intercontinental network of radio telescopes that work together in a method that is called very long baseline interferometry. So when you have a regular radio telescope, it's basically a dish, like a kind of satellite dish you would use to receive TV signal from the satellite. That is pretty much the same thing, only the dish is larger for a radio telescope, and it must be made more carefully with the care about the quality of the surface. But it means that the sensitivity is limited by the size of the dish. So if you, this is sensitivity and also resolution, they are both limited by the size of the dish. So if you want to have extreme resolution, this is not something that you can achieve with a single dish. What we need to image an object like M87, we actually need a dish of the size of the Earth. And this is, of course, technically extremely challenging. You will not build a dish the size of the Earth. But
you're not going to get funding for that.
I mean, we didn't try. But I would expect to fail if we did. So the next best thing you can do, you can find a bunch of telescopes in remote places, far away one from the other, and join them, virtually merge them into an array in a way that your dish is really your planet. But on this dish, you mostly have an empty surface. You don't have an active surface everywhere in the dish. You have just a little bit of sensitive part of the dish here and there. And this here and there are our radio telescopes. So we have a little bit of active surface of the dish on the South Pole, in Greenland, in Mexico, in Hawaii, Arizona as well. Other than that, it's an empty dish. But it turns out that this is sufficient to get enough information to image an object, provided that you get an additional boost. An additional boost is something that is called an aperture synthesis. It's just the fact that the Earth is rotating. And as the Earth is rotating during the observation, the geometry between one dish, another dish, and the distant object in the sky is changing. So because the geometry is changing, you get to get more independent measurements. So really, it's a bunch of stations in different locations around the Earth, plus the fact that the Earth is rotating. Also notice that it's important that the Earth is round and rotating. So this is also on the side, we are kind of confirming this very controversial recently opinion that the Earth may be round and may be rotating.
And so as we go...
It shouldn't be controversial.
It should not be controversial now. And can you tell us about some of the future studies and upcoming instruments that may be able to be used to help search for black holes?
So there are very nice upgrades planned for the Event Horizon Telescope. So the data that we have shared with the community so far, it's everything up to 2070. We actually did observations in 2018. And in these observations, one station joined that was not present in 2017, and that's the Greenland telescope. So because M87 is seen in northern sky, Greenland telescopes actually does amazing things for the M87. So in 2018, we have obtained a much more rich data set of M87 that we are currently still working on to process that data set. Well, then unfortunately for 2 years we didn't observe in 2019 and in 2020. In 2020 for the reason that, well, nobody was able to do anything in April and in March. But we hope that next year we will be able to get back to these routine observations every year. And there are 2 stations that are joining in 2021. And those stations are NOIMA in France and Kikpik in Arizona.
Yep.
Well, because the number of detections that we are getting, it depends on the number of pairs of telescopes. It's not one telescope that makes the measurement. This sort of measurement is made between pairs of telescopes. So it means that if you add 2 stations, you really get much more independent detections, because you get detection from this new telescope to every one that is already there. So every single addition is a huge benefit for us. So we hope that 2021 will actually be absolutely amazing and better than anything that we had so far.
That's fabulous. Well, thank you so much for being on the show, Maciek.
Thank you. That was a pleasure.
Wonderful to have you here. And that was Dr. Maciek Wielgus of Harvard University. Next week on Astronomy News with the Cosmic Companion, we'll talk to Dr. Roberto Chili of the National Institute for Astronomy and Astrophysics, joining us from Italy. We'll talk about his recent discovery of 6 galaxies huddled around a supermassive black hole in the early universe. Make sure to tune in for this interview starting October 20th. Join us each week on Astronomy News with the Cosmic Companion as we bring space and astronomy news together with groundbreaking scientists directly to listeners and viewers around the globe. We depend on support from viewers like you. To help support this program with a one-time donation or a paid subscription starting at just 99 cents a month, please visit thecosmiccompanion.net/support. If you live in the United States and have not already done so, please remember to vote this election. And please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of Astronomy News with the Cosmic Companion, please download and share the episode on YouTube, Facebook video, or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.